In this video, we're going to be looking at related rates. Related rates are similar in a sense to implicit differentiation. So as a warm-up, just to get our brains going again, if I start with x squared plus y squared equals z squared, and I want to take the derivative with respect to time, so dx dt, dy dt are given. They want me to find dz dt at a specific moment when x equals 3 and y equals 4. So I'm going to take my derivative with respect to time. So this would be 2x dx dt plus 2y dy dt, and that equals 2z dz dt. Now I could simplify. I could divide everything by a 2. My 2's will be gone. All right, I'm not just crossing them off. If I factor out a 2 from the left and then I divide both sides by 2, that's how the 2's are becoming a 1. And now I'm just going to plug in. I'm trying to find dz dt. So I'm going to plug in everything I know. All right, so plugging in what I know x is 3, dx dt is -2. I know y is 4. I know dy dt is 7. But I come over here and I go, oh, wait a minute, there's nothing to plug in for z. I didn't get enough information. But we did get enough information. So we know the equation, x squared plus y squared equals z squared, and I know x and y, I can solve for z. So I can say 3 squared plus 4 squared equals z squared. So I have 9 plus 16 equals z squared. So z will equal 5. I'll get z squared equals 25. I do know my z. They tried to trick me, but I know it. Z is 5. And I'm looking for my dz dt, so I leave that alone. And now I'm just solving an equation, and over here is the variable I'm solving for. So I have -6 plus 28 equals 5 times my dz dt. -6 plus 28 is 22 equals 5 dz dt, and then I'm just solving both sides. So my derivative for z with respect to time dt is 22 over 5. Now when we're dealing with related rates, we're doing similar things. We're going to have given information, we're going to be looking for something specific, but we're going to be taking our derivatives with respect to time. Okay, so here's our first related rates problem. It says water is being poured into a cylindrical tank at a rate of 4 cubic centimeters per second. If the radius of the tank is 10 meters, how fast is the depth of the water changing when the water is 3 meters deep? So first thing you always do is you want to make a clear picture. So it said I have a cylindrical tank. So here's my not great drawing of my cylindrical tank. Okay. I am trying to find out how fast the water level is changing. Okay, they told me the radius is 10 meters. Now, on my tank, that radius of 10 meters is never ever going to change. That is a fixed constant. Now it said water is being poured in. So here's my water coming in, and it's bringing it to some level that I don't know what it is. So I have some level in my tank of water, and it said it's going in at 4 cubic meters per second. So 4 meters cubed per second, that's how fast that water's going in there. It said the radius was 10 meters. They want to know how fast is the water changing, so the height, so the change in height with respect to time, dH dt is what I want. How fast is that changing when specifically the height is 3? Okay, so we've got to figure this out. So our strategies when we're attacking related rate problems in general is to always draw a clear picture of the situation. We don't label it with any numbers right off the bat. We have to first figure out what are we looking for. So for this one, we're going to have to write an equation. And to figure out what that equation is, we have to identify the concept that's being relevant to the problem. So in this last one, we're talking about a cylinder, and they gave me cubic meters as my units. So I know it has to do something with the volume. Then I'm going to label the picture with the constant dimensions, which we did. That was that radius. And then I labeled picture with the variables in the equation. I labeled the rate, and I didn't label the h. We're going to go back and label that. And then once I get everything set up, I want to differentiate my equation with as few variables in it as possible. Okay, so here's our picture again. We have our strategy. We know we need to come up with some sort of equation, and then we can differentiate our equation. So we're talking about a cylindrical tank, and we said the rate that water is going in is 4 meters cubed per second. So that meters cubed, this is filling something up, we're talking about volume. The volume of a cylinder is given by pi r squared times h. Now, for this problem, my radius is fixed. The radius never changes. The volume depends on the height, and the height is changing depending on how much water is in the tank. But even if it's empty, that radius is still 10. So I'm going to rewrite this by plugging that in. So this is pi times 10 squared h. So my volume is 100 pi times h. Now I have my equation. I have it with the minimal number of variables I need. Now I'm going to differentiate it. So my dV dt, my change in volume compared to time, is equal to 100 pi dH dt, change in height compared to time. And we want to find dH dt when h is equal to 3. Well, we know our dV dt is 4. Excuse me. I know it's still 100 pi. And at that moment, it doesn't change my dH dt. So I can find how fast the height is changing regardless of at what second I'm at, because the rate going in is staying constant. So to get my dH dt, I just have to divide. So this would be 4 over 100 pi. I always simplify. So this gives me that the height is changing at a rate of 1 over 25 pi, I wrote pi, meters per second. All right, water is leaking out of a conical tank of radius 20 centimeters and height of 40 centimeters at a rate of 15 cubic centimeters per second. How fast is the radius of the water changing when the radius of the surface of the water is 17 centimeters? Okay, so I have a conical tank that kind of looks like an ice cream cone or a snow cone. So here's my conical tank. We said water is coming out, there must be a hole in the bottom at a rate of 15 centimeters cubed per second. So that's a rate. When I have distance per time, this is the rate. And we're talking about a water level in here, so we know this is a volume. So that's my dV dt. Okay. What we want is dr dt, how fast the radius is changing, and we want that specifically when the radius is 17 centimeters. So they told me the fixed is that at the very top, this is a 20 centimeter radius, and the overall height of the whole thing is 40 centimeters. And we want when the radius is 17 centimeters. So I don't really know what that height is there, right? We have two heights. So what we have to do here is we have to eliminate a variable. We can't have two things that are changing. When I write my equation, the volume for a conical tank is 1/3 pi r squared h. So I have an r and an h. And I need to kind of know what that h is. I don't have it fixed right now, but I need to know what it is when that is going to be 17. So that I can figure out. But I want to eliminate as much as I can. So I'm going to use similar triangles. And I know the radius is always in proportion to the height. So the original radius, I'm going to come over here, is 20 when the height is 40. So I can get, for any instant in time, the radius as a function of height, or the height as a function of radius. So I'd have 20 height equals 40 radius. So my height is always equal to twice the radius, no matter where I am, at what point I am filling or emptying this tank. So I'm going to rewrite my equation, and I want to eliminate that h. I want as few variables in the original problem as I can, because none of them are fixed. I can't just ignore it until I get there. So I'm going to rewrite this as volume equals 1/3 pi r squared times 2r. So cleaning it up, I have 2/3 pi r cubed. So now that we have our equation with only the two variables, we have all our information, we can take our derivative. So we have dV dt equals 2/3 times 3 is just going to be 2 pi r squared dr dt. And then I can plug in and solve for my dr dt. So dv dt we said is 15 equals 2 times pi times 17 squared dr dt. So I have 15 equals 2 pi times 289 dr dt. And then I just have to divide. So coming back over here, I'm kind of running out of room. When I divided 15 by the whole thing, 2 pi times 289, I end up with my dr dt is equal to 0.00826, and the decimal keeps going. And I would say that this is changing at a rate of 0.008 centimeters per second. So dr dt, final answer I'm putting up here so we can see it, is 0.008 centimeters per second. In this problem we have a ladder that's standing against a wall. It's a 4-meter ladder. The foot of the ladder is falling away. It's moving out from the building at a speed of 0.1 meters per second at the exact time that the bottom of the ladder is exactly 2 meters away from the wall. We want to know how fast the top of that ladder is falling. Hopefully nobody is standing on it. So here's my wall. Here's my 4-meter ladder. The ladder is fixed. That is never ever changing. Okay? And here's my ground. And we said that the ladder is moving out at a rate of 0.1 meters per second. Okay? So we want to figure out how fast is it falling down here? How is that height changing? Well, if I notice, I'm looking at a building compared to a sidewalk, so this is a right triangle. So this is dealing with Pythagorean theorem, a squared plus b squared equals c squared. Now in this case, my c, that's the 4 meters, this is fixed, but my a and my b are going to change. So we said specifically, we want to know at the exact moment that this is 2 and this is 4, we can figure out what that missing side is. So if I call that side b, I can say 2 squared plus b squared equals 4 squared. So I have 4 plus b squared equals 16. So my b squared equals 12, and I know b equals the square root of 12. And I'm going to leave that like that for now. Yes, I always simplify radicals, but that I'm going to be using in the problem. So I'm just going to let that go for a minute. So now I know my fixed, I'm going to plug that in. So I have a squared plus b squared always equals 16. And I know that a is changing at a rate of 0.1 meters per second. Now this is getting bigger. This is a positive, right? Over here, the b value is going to be shrinking. So when I take my derivative, this is 2a dA dt plus 2b dB dt equals 0, because that is a fixed constant. That is never changing. Now again, I can factor out my 2, so the 2's are gone. And I'm trying to find dB dt. So I'm going to plug in what I know. So when a is 2, its rate of change is 0.1. When a is 2, my b is the square root of 12. dB dt equals 0. And then I'm just doing a little bit of algebra here. So I'm going to end up with dB dt equals my 0.2, a negative because I'm subtracting it over the square root of 12. So it makes sense that it's negative because that distance is decreasing. And then when I calculate this, negative 0.2 divided by the square root of 12 is going to be negative 0.057735. It keeps going. In a specific problem, we make sure we round correctly. I'm going to round to 2 decimals. So dB dt, the rate that the top of the ladder is falling, is negative 0.06 meters per second. Okay, the last example is an aircraft is flying at an altitude of 3 kilometers at a speed of 600 kilometers per hour in a direction away from a tracking station. How fast is the angle of elevation changing when the aircraft is over a point 8 kilometers from the station? So again, we start with a picture. So here's my plane. I'm a terrible artist, so that's my plane flying. I guess I should give it 2 wings and its tail. So there's my plane. Really bad picture, I know. And he is flying away from a tracking station. Here's my tracking station down here. He's flying at an altitude of 3 kilometers per hour. So that's a fixed distance from him to the ground. It doesn't matter where he is, right? I can't do that. He could be directly under, it doesn't matter. He's always 3 kilometers above ground. So this is fixed. We always like to know what our fixed things are and what's changing. What we want to know is how fast is that angle of elevation changing when he's 8 kilometers from the station. So angle of elevation means if I'm standing here and I'm looking up, it's how far up from the horizontal I had to look, right? If I'm way over here, it's going to be a really steep angle. I'd be looking straight up. The further over he goes, we'd have a much smaller angle. Kind of going in this direction, I'd have a much smaller angle versus this versus this. So the angle is changing. So we want to figure out what that angle is. So now we have to use some trig. So for all related rate problems, you're working with some sort of geometry, right? Triangle trig, area formulas, volume formulas, Pythagorean theorem. It's all something related back to your geometry. So in this case, we have to use some sort of trig values. So we want d theta dt. I use theta, that's what I've always used. You can use an x, it doesn't matter. So we want d theta dt, how fast the angle is changing when my distance, this vertical distance is fixed. We want that when this horizontal distance is 8 kilometers. And I'm putting an h there just because I'm calling that my horizontal distance is 8 kilometers. Well, so this is fixed. We have this side and this angle. So this is the opposite side and the adjacent side. So this is something to do with tangent. So I'm going to write a tangent equation. So I know tangent of an angle is equal to my opposite, 3, over my adjacent, which in this case I said I'm going to call h. So h is fixed. Excuse me, h isn't fixed. The 3 is fixed, not touching that. H can change, my angle can change. And it specifically wants to know that how the angle is changing when the height is when my fixed, I keep saying h for height, my horizontal distance is changing at 600 kilometers per hour. So I know that dh dt at that exact time is equal to 600 kilometers per hour. So in order to figure this out, I can't replace either of those variables. They both depend, they're both there. I can't rewrite one in terms of the other. So I'm going to have to take the derivative of both sides. Now, I don't really like having to take a derivative of 3 divided by h, but I'm going to because I prefer to do that than have to do the product rule with 2 variables. So I'm going to take my derivative. Okay, so derivative of tangent is secant squared theta times d theta dt. And over here, my derivative is going to be, this is 3h to the negative 1, so it's going to be negative 3h to the negative second. Okay, so if I clean this up a little bit, secant squared theta is really 1 over cosine squared theta, so I have d theta dt all over cosine squared theta equals, on the other side, I have negative 3 over h squared. So if I clean this up a little bit, I'm trying to find d theta dt. I know that d theta dt will equal negative 3 cosine squared theta divided by h squared. Okay, I know my h is 8, but I don't know what theta is, do I? Well, I do, because at that exact instant, I can calculate my exact value of theta. So if I want to know the exact value of tangent theta when my opposite side is 3 and my adjacent side is 8, I'm going to have to do tangent inverse. So theta equals tangent inverse of 3 over 8. Now this is a calculus class, so we have to do everything in terms of radians if I go to plug in my angles. But if I'm working with a calculator, I can type in cosine squared of tangent inverse of 3/8. It will keep the units the same. You just need to make sure your answer is coming out as a radian, not in degrees. So we need to be in radian mode. Okay, now I don't like to round until the final answer, but so we can make sure your calculations are working. When I calculate tangent inverse of 3/8 in radian mode, it comes out to be 0.35877067 are all the digits I can say in a calculator. And then I'm going to take the cosine of that and square it. So I'm going to come down here. I'm looking for d theta dt. So I have -3 times, I'm pressing cosine in my calculator. So cosine of the 0.3587767. And then that's giving me 0.936, blah, blah, blah. And I'm squaring that. So that's giving me 0.876712329. I haven't rounded anything that I could see, and in the end we're not going to round out to 8 decimals, so we're okay. Our h value is 8, so 8 squared gives me 64. So I'm going to multiply my numerator by that 3, and then I'm dividing by 64, and I get that d theta dt is equal to negative 0.04109589. Those are all the digits on my calculator. And then I'm going to round this time. It didn't tell me, but I'm going to round to 2 decimals. So d theta dt for my answer is equal to negative 0.04 radians per kilometer. Or excuse me, radians per hour. There we go. Sorry. Watch your units. Don't mess up your units. Okay, so my final answer is that the angle is changing at a rate of negative 0.04 radians per hour. And that makes sense, because if the plane starts up here, it's a really big angle, and as the plane's coming further and further away, the angle is getting smaller and smaller. So that negative on my answer is telling me that it is decreasing. It's getting smaller as it changes.